Hello, I'm Christina and I'm the team leader of CTU Robotics, and this is our main project, Rover Barum Gen 3. We are a student team from Czech Technical University in Prague that consists of more than 50 members, mainly from Faculty of Mechanical Engineering and Faculty of Electrical Engineering. Our team was formed 3 years ago, and for the very first time, we want to participate in the ARC not only to compete, but also learn, improve, and test our limits. We selected our astronaut from our team members based on their understanding how the rover works, as well as their ability to troubleshoot, operate, and repair the system under pressure. Training of the astronaut focuses on precise control of robotic arm, rover itself, manipulation tasks, and effective communication with base crew. Our rover is designed, assembled, and tested in our university workshop that's located in the building of Faculty of Mechanical Engineering. We test everything we can indoors, such as basic functionality, system integration, and communication, before we move outdoors. There we test the rover in real terrain, including animal surfaces and natural obstacles.
The mobility system of Rover is based on rocker kinematics. With a wheelbase of 850 mm and low center of gravity localized under the main frame, Rover maintains excellent stability in rough terrain. These design choices allow the rover to climb and traverse through slopes exceeding 40 degrees and navigate various obstacles with ease. To connect the rocker with the differential bar and the frame, we utilize durable and lightweight plastic plain bearings generously provided by our sponsor Henlich. A unique feature of our wheel design is integrated grounding system, which protects all onboard electronics from static electricity. The entire chassis is fully modular, ensuring that repairs are simple and remarkably fast in case of failure. Our primary focus was on weight reduction. By optimizing the use of lightweight materials such as carbon fiber, aluminum, and 3D printed parts from PETG or PC blend carbon fiber, we successfully reduced the rover's total weight by over 25 kilos, compared to the previous generation. All electronics are housed within a sealed frame constructed from aluminum profiles. The frame has several mounting points for additional systems, such as the robotic arm, drilling tool, or cam tower. For the internal layout, we implemented a newly designed modular system to secure all electronics.
Every subsystem in our rover depends on reliable power and data. Our job is to make them flow both reliably, without interruption, even under the harshest conditions. At the heart of the power system sits a custom assembled battery pack built from high-density lithium-ion cells. At 12 amp-hours and around 40 volts nominal, we got approximately 500 watt-hours of continuous energy. A commercial BMS handles cell balancing, thermal protection, over-current protection, and much more, so we never push the cells over their working limit. Power distribution is managed by our custom-designed PSU PCB. It includes step-down converters for sensitive electronics, switchable outputs for power routing, and real-time current monitoring at every branch. It is also the core of our hardware safety architecture. The PSU directly interfaces the emergency stop button, which instantly cuts power to all motors. For locomotion, we use BLDC motors with integrated drivers and planetary gearboxes. They communicate over a high-speed CAN bus. For low-level sensor integration, we use microcontrollers with network connectivity, so there is no need for additional USB or serial bridges. Our primary data link is a Wi-Fi access point. If that degrades, we switch over to LoRa for critical telemetry. For real-time manual control, we use a dedicated FPV feed, prioritizing latency over quality.
Our manipulator is a robotic arm with 6 degrees of freedom. We use map motors with rotary encoders in every joint. We have a set of end effectors that we can switch between, for example, basic gripper or a digger. There will be a camera mounted on the gripper, which we can use to get image data or a point cloud. We can further use that for autonomous behavior or planning trajectories with collisions. The arm has its own detached Raspberry Pi, separated from the main rover, which runs ROS2 and MoveIt2 for planning the trajectories, and it also runs a servo node for manual operation.
Our drilling system has been designed as a two-level movable console. First, the outer structure reaches the ground, and then the drill bit is engaged. This minimizes system's protrusion to the ground clearance, as well as reducing the stress on the drill. Design measures to minimize soil loss during extraction have been implemented too. A plexiglass tube encloses the drill bit, and the lid closes the tube as soon as it exits the soil fully. The system's capacity is 300 grams of soil at a drilling depth of 30 centimeters. After successful drilling, the soil is deposited in a sealed container capable of measuring weight.
Parent control stack is built from ground up to support both manual and autonomous operation through the shared interface. Our aim for ARC 2026 autonomous mission is to fully rely on our autonomous layer, so every decision is made on board from the moment the rover leaves the airlock. That ambition rests in redundancy at every level. The compute is split across 3 machines. 2 Raspberry Pi boards handle real-time motor control on the robotic arm and the rover base, while onboard computer with Intel processor and 32 GB of RAM runs SLAM, sensor fusion and mission logic. For perception, we rely on 2 Unit 3 LiDAR units, providing us with nearly 360-degree coverage paired with RGBD camera and inertial measurement unit. For localization, we fuse wheel odometry, visual odometry and inertial data through 2-layer extended Kalman filter. First layer keeps our short-term pose smooth, while the other anchors us globally through our landmarks. On top of that, AirTap map builds consistent 3D map in real time. Nav2 stack plans a global path and continuing replanning that path locally at 20 Hz, allowing us to avoid any obstacle at any time. Mission logic runs on a behavior tree that can communicate with RSCP. This means every objective, like provide coordinates, go to GPS or go to final pose, maps onto action node, with failure handling built into structure itself.
To be able to give a detailed account of the geology of the region in the science mission, we have devised a suitable scientific platform capable of both direct and indirect analysis. When developing scientific instruments, we focused mainly on the ongoing scientific debate about the longevity of hydrated geological system in Athabasca valleys. Optical sensors serve not only to guide our rover, but also to differentiate various geological landforms in the environment, alongside their properties such as size, color, lithological structure, and texture, all while relaying this information directly for ground analysis alongside the telemetry. Our drilling tool allows us to reach depths of up to 30 centimeters and collect samples unaffected by surface aeolian weathering processes. These samples are then analyzed by our science package, gathering information about their size, weight, density, color, structure, and texture by means of close-up photography. Sealable analytical boxes are used for onboard analysis and material transportation from the drilling and sampling sites to our ground analytical lab station. Both wide area observations and direct material analysis are needed to fully grasp the geological development of the region. Fundamental understanding of the underlying mineralogy in the region is paramount for correct sample analysis and verification. To this end, the geologists and chemists in our team are working on an addition to our science box capable of identifying specific mineral groups.